Oh, what's going on? What's going on, penoids? Whoa, fucking. Let's see my audio. Yeah, okay. I need. I was gonna do work. I'm feeling fucking, bro. This shit goes on forever. Like, it's just it's all for. I've never heard of Fourier optics. I don't even know optics. I had to look up the lens equation, bro. I don't know any of this shit. Like, it's like, what is like? There's a new fucking like. Dude, it invented a new mathematical operation I had not heard of before. Like, let me try and fucking. It was like. Oh wait.
So in this video, we're gonna talk. This is Fourier optics.
Here it is.
Field, and we're in of x of s convolved with.
Convolved. What the fuck does convolved mean?
Actually, in this case, it's just xs. E to the jk xs squared over 2d. So we've also got an a naught out front. So we can rewrite.
Wait for the tone of his voice. Wait for the tone of his voice.
That tells us that we've got our input spectrum, or it's not our input spectrum, but our input field, and we're sort of just smearing it out with this phase term, and it's not exactly clear what that means at this point. But we know if we don't want to deal with convolutions, or if you don't know this, you should really take a class on the Fourier transform, because this is Fourier optics.
The way he laughs like that, bro. Because it's clearly Fourier optics. Bro, like, it's clearly Fourier optics. It's so obvious that you just have to do a Fourier transform to turn a convolution to a multiplication.
Into multiplication.
Yeah, fucking eat my fucking nutsack, bro. So now I've just accepted it to be true, and I'm going back. So like, oh, so I started off. I got to here. I was like, oh, I don't get this. Time to go to the first one. Oh, I don't get this. But I'm not. Just continue watching this.
Fresnel and Kirchhoff here, civil engineer and physicist. Fresnel.
I always call it Kirchhoff, not Kirchhoff.
Him dying young. And here we have.
He did die young, 39. Oof.
Physicist, known for the laws.
Double my age. I'm halfway through.
You're doing circuits if you have a junction like this.
And you see how this is his equation here. See how it's like looks completely different. Like they all look so different to each other, and he includes the obliquity factor for this one.
And here I2 and I3. You can
Ooh,
write
bro.
I1 is equal to I2 plus
Why is he talking about the current laws? This is not current. This is not fucking electricity. What's the policy? What is blood talking about?
Say I1 plus I2
plus
I3
equals 0. Yes, I'm so got it.
Say I1, I3, and I2. The currents algebraic sum giving you 0. Or you can say what comes in must go out. And then the voltage law.
Please tell me this relates somehow to this.
Say a battery. And then say you have a light bulb and a resistor. You go across the battery, say V naught, and then you could voltage across. U2, wavefront and optical path. So let's consider a wavefront here. Origin, say, at point O.
I'm going back to drawing, doing this thing.
Distance here, and another distance over here on the axis. This is on the axis. Point P, and point O, and we'll call this A, and we'll call this B. So if we go up to this point up here.
I've already done this.
And then drop a perpendicular down there.
I haven't.
And let's consider this as a radius.
Oh yeah, I've definitely done this.
You have a circle here if you swung all the way around. Here you have the source of the waves, coming out. We'll call this R prime. Let's call this H prime.
Yeah.
And here, this has.
Right, he's been explain this.
This is
Oh my, yeah, because oh my god, the assumptions they make are so fucking infuriating.
because that's the radius. But then R, to go from the point P all the way to here, would be delta plus B.
Mm-hmm.
So that delta, that's important. That delta is going to be our extra optical path compared to the reference. Like if you were simply going this way, like if there's a crest here, and then you got this optical path, the crest would be up here, so who knows what would be there. So it could be a crest or trough or something in between. So let's drop another perpendicular here, down, call that H. Then this little piece here, let's call that delta prime, with the lowercase delta, and this delta. For small angles, by the way, this R prime is equal to A also, since that's still the radius.
Yeah, here, wait for this bit.
For small angles, this delta, big delta, is going to equal the sum of these two.
So
It's gonna
true.
Not be so high up. So
I
we'll
fucking
make that
hate approximations. I hate
This is gonna be
approximations.
delta, little
Like,
delta plus.
that makes sense. I get that. You know, it's like, you know, actually I can't see it, but it's, you know, it's just like you're just collapsing it in. But like, when they do not make assumptions, it does not seem like fair. It doesn't seem like, you know, there are times when like I think an assumption would, you know, make sense, but it doesn't work, and there's times where it does work, and it really isn't
Little
properly
delta.
explained what makes it
We'll
break, you
put a
know.
on one of them, first one there.
Because I get why it makes
And
sense,
then remember,
but to be other situations
R
where I think the same sort of thing would make sense, but it just doesn't work.
is equal to big delta plus B. Now it's kind of fun to find these deltas if you're looking at like this here, and from we'll take the triangle over B, and here you have it H squared over B squared. Put B back in, you get B squared. B squared's cancel.
We didn't
you
have a
get
thing for this one. This one we did
what
something
you're
different.
supposed to get. So now with the small angles, in other words, close this down, because you were making the approximation as big deltas is some of the small deltas. Then when you do that, you can do the Taylor series expansion, and this is going to be 1 minus 1/2 H squared over B squared. To make this
I hate the Taylor expansion. I hate everything.
So now if you
Oh,
look at this, you have
Taylor
B
expansion.
minus
So
the B
obvious, bro. She's a Taylor
and a
expansion.
plus.
Scratch my fucking
One of
balls.
the B's are going to cancel. This is 1/2 H squared over B. So this is 0, and you have for the delta, and you know we could say approximately because we are doing Taylor series expansion here. This is 1/2 H squared over B, and the one on the other side is 1/2 H prime squared over A.
Yeah.
That's on the other side here. You know, where you have here the A.
And so you add them together, yeah. Because that's where they pull this shit from.
A. You play the same game.
They just
And also
do it
for the
here. They just
small
fully skip it.
angles, the H's are pretty much going to be the same. So we take the
So hopefully, so I think I've done most of the stencils. Yeah, that's looking good. That's looking good. I'm understanding this.
and this angle is very, very small. A agrees with R prime, B agrees with there, and they're like delta 0. So let's look at this and compare with the wavelength to see what's going on. Because for that delta to appear to be 0, you really want it to be compared to the wavelength of light. That compared to the wavelength of light, you know, crests and troughs, basically, that delta is 0. So if we look at a diffraction gradient, for example, that the fraction gradient can have 250 little slits, 250 lines per millimeter. Like that to be, say, the H. So if you do that, then in this formula, you're going to have some to the meter, 10 to the minus 1 meter. So your lines 10 to the minus 3 nanometers. Wow, that's 3 like over 1,000 nanometers. Well, that's a lot less than, say, visible light, middle of the spectrum, somewhere like where most sensitive to light is at 550 nanometers. That's very, very small.
I like that how this guy
Fraunhofer diffraction.
explains it a bit more. Yeah, there's
Or
some.
Fraunhofer far field. So we have then the far field, which would be Fraunhofer, and then what we're going to be studying in the next few classes here, near field. It's going to be Fresnel.
Fresnel, fucking.
And if you get real close to the source,
But like no, like Fresnel, bro. Where is the S? Like Fresnel, Fresnel, sucker.
that would mean you have the slit like this, and there's some source back here.
I can't believe I'm gonna get no fucking sleep,
You're in the
bro.
face, you then get blinded by the light. So in other words, the extreme near field in your face. I'm just going to say blinding light. So you're not going to get like lights in dark. You're going to get blasted by all the light. Then when you back away, you'll have the diffraction effects. So now we go to the book now for a school diagram where you're looking at the spherical wave, the mother wave here, and we're looking at concentric regions so that when you look at the extra path length, you add a wavelength over 2.
Yeah, that makes sense. Yes, I've done this.
The structure path formula things. Now for this small,
Here, go back a bit.
in our book, this is the master formula we already derived. Showed you where it came from. And this one here is one we already set up also. The only thing we're doing is replacing h by the radius, since h was that measure in the up direction. So we're basically letting the h be the radius, and then we're using a little m on there because we have different ones for like different sizes. So the A becomes Z prime, the B becomes Z. So this is our adapting our formulas. So they're the two things. Now for the small radii, now I'm using capital R, for the radii, going away from the center here. Okay, so these are the equations we had before, and if I make the approximation that the R prime and Z prime are roughly the same, R and Z, because this distance is very close to this distance, then I can replace R prime with Z prime, R with Z, and pull it out of the equation as a constant. Look at that. So EP is equal to the integral of the aperture, E naught. This is our equation we had earlier. And the approximation here, R prime, is going to be like the Z prime. R is going to be like the Z. Now we make that approximation down here in the denominator, but we're very careful up in the top here not to do that because of the cosines and sines. See, this is large, you can get away with that, but you don't want to mess around if you're doing cosines and sines because of the oscillations. So for the angle being small, this becomes a 1, and we get for the point
But I swear I've already done this.
here,
Whoa.
E naught over z prime integral e to the I k r prime plus r dA. So that's our formula now. Now, if you want to consider one of the zones, like
See, this is where it's here. So you just times the entire medium by that. You take a
just pick one. Then for one of the zones, there's going to be, some big R in the radius. And you're going to have this setup where on this side you have
maybe I'm the only one for
this is going to be our
me.
Z prime. This is our Z.
I always
So if you go up
at
there,
the end.
this is going to be an R prime to get up there. This is going to be an R to get back down. So you got yourself here 2 triangles. You're going to have
Oh, I don't understand the assumption. Like, he's assuming something, then undoing the assumption. R prime equals Z prime, but like for some reason we want to keep them separate in this equation because they're actually not the same thing. Because we just assumed it is. Like, eat my fucking scrotum.
this is the R prime here, hypotenuse, so R prime plus R. These are 2 hypotenuses, so you're going to have Z prime squared plus big R squared to get this one. So this is the R prime, this one here. And then we're going to add to get the other one, since that's what appears up in here, that's what I'm interested in. This is the big R squared.
Yeah, 'cause I don't get how to get from here to here. So this goes to 0. You if you want to add 2 fractions and have that at the same denominator, so you times this one by R, this one's by R dash, and you add them. So it should be e to the kr this should be times by R, it should be times by R prime. For some reason they just pull out the denominator, which makes sense. Let me try and do the maths on this, if I like. Yeah, I don't understand because it's R e to the I R prime or K. I'm using rho because I was using rho before for R prime plus rho e to the I K R Actually, no, they're being multiplied. Oh my god, they're being multiplied. Yeah, I know. I'm straight just retarded. Yeah, that makes so much. That makes perfect sense, actually. Yeah, I'm straight retarded. I'm straight retarded. This to me. Yeah,
Plus
you
the
just
z
boom together, turns to a plus. Yeah, okay. Oh, it makes sense. That equation makes sense now.
Okay, so you have to be careful up in here. So then we can write down r prime plus r. We could pull out the z prime.
Just doing this whole z shit though, so fucking melons. Like I don't understand.
And if we do that, we'll have a big R squared over the z prime squared.
Yeah, because like here, to convert this into this, they're saying big R is obviously gonna be 0. But then like later on they assume it's not 0. Like the assumptions are inconsistent and it annoys me.
It is. Squares cancel there and you get the R squared. And do the same. You're gonna get 1 plus
Well, I'm just like
R squared.
this fella about to use the Taylor series again.
The 1/2 power. Now, this R is definitely small, big R, compared to the Z and Z prime. So now we can do the expansion and have 1 plus 1/2 R squared over Z prime squared. And then this is going to be...
Bro, these guys need to marry the fucking Taylor expansion, bro. Fucking gay asses. Constantly using it.
Then we can kick the z's back in, and that's going to get you a z prime, and this is going to get you a z. We'll go ahead and write these out first, and then we're going to have r squared, big R squared over 2, and we're going to have 1 over z prime plus 1 over z. So let's check this. Z prime, that's this one here. Z, that's that one there. When you bring the Z prime in, one of the Z prime squared, you're going to kill one of the Z primes there. So you'll have the 1/2 capital R squared, and you'll have the 1 over Z
That makes
prime.
sense, that makes sense.
Same thing over here going on. And pull out that common R squared over 2, and so you get this formula.
I feel
nice.
There's a... Probably because I drank loads of coffee, yeah.
That
My stomach feels
this
weird.
part here, remember when that was our h over h squared over 2, and this was our, the a and the b. This is the extra path length. That's what that is.
Yeah. Like, that makes sense. But we, like, just assumed previously. It was like... R squared, this is... S squared is this, so that's basically that's the h in this one's. You think so? R squared yeah, makes sense. R squared over 2. Okay, that does make sense actually, but there's a 2 there which shouldn't be there. You don't do this like this. Actually, no, if you do this. There's 2a. S squared 2a. Delta equals S squared, which is just the S's are R over 2. Oh wait, no, that makes perfect sense. Yes.
That's very nice that it showed up like that. So that means we can write e to the I, k.
I don't really get this. I guess it's a solution to the wave equation. The wave equation, I've got the actual meaning of it is now, but it's like you need it's some fucking second derivative symmetry type shit. So you need the I in there.
As e to the I, k, z prime plus z plus the delta. Beautiful. Now that showed up like that. Alright, that's what we had earlier. Just to show it. Look, here it is. where we did that. So your H is your radius. Here's your 2, and the A is the Z prime. The B is the Z. That's it. All right, and then we can let that R be like different ones, and have the subscript on there like we did earlier. So this means that if we go back to our formula EP, here's the formula here. So we're going to look at E naught over Z prime, and then the integral that we're going to have here is going to be E, this E to I K, this sum here, we're going to write that as I K Z prime plus Z, and just pull out this delta part, I K delta dA.
Z prime is there just the base things in this, so if I go back to here, get the scoopity scoop. P R. Yes, that makes sense, that makes sense, that makes sense, that makes sense. Because it basically P R, P plus R dA, and that is equal to the same thing, E naught over R O P O integral for the entire area of E to the I K, and it's P O plus R O plus delta dA.
You have that cool formula. We just simply put this back in here is what we did. So we have the stuff out in front, and then putting that in there, and just separating out the delta part since the exponents add. When you multiply, you have this equation. Now notice that this is a constant. This is beautiful physics here to see all this. This is...
Wow, his voice is... his voice is weird. That's getting beautiful physics out here.
Now notice that this is a constant. This is beautiful physics here to see all this. This is an E naught over Z prime, E to the I K, Z prime plus Z. And now it's over the aperture.
Oh my god, yeah, they are. Oh my, actually, but that actually some beautiful physics. I'm about to fucking come. Holy shit. Yeah, look at that. I was in the sword drag going, some beautiful physics out here. This is some beautiful physics. Holy fucking shit. Oh my goodness gracious.
You have E to the I.
Then if I go back to the previous one somewhere, where they have this, and then it's like, yeah, and then it's like.
And then from before, this delta, we can put a little subscript M on there, and then we would have an R squared to the mth case over 2, and then we would have the same 1 over Z prime plus 1 over Z in there. And remember that when we do this, we're just reminding everyone this is M.
Yeah, it's looking vaguely similar.
Lambda over 2, because every time you go to one of this concentric rings, you're adding, M for the, basically like the edge is going to have M lambda over 2, like we saw earlier. We can define this to be 1 over L, capital L, and we can even combine them, Z prime Z, add them up, common denominator. You get this, Z cancels. First piece is 1 over Z prime.
I don't get why, because like 1 over L represents 1 over the focal length. Please just use the normal symbol for focal length, like.
And when you have this will cancel, you have 1 over Z. That's nice. Alright, so the L is equal to Z prime Z, we're flipping this, over Z plus Z prime. So let's look at this more carefully. If we do this, and use this substitution, then this is going to be a nice compact formula. Delta of m is going to be the rm squared over 2, and this is 1 over L using our definition. Cleans it up a bit, and that's m lambda over 2. So this means that the radius of the Fresnel zone is going to be equal to, the 2's cancel, the L goes over here, so you have this cool formula, m lambda L. And then if you want the radius, you would take the square root of m lambda L. Nice.
1, 2, 3.
Now, if you want the area, you have pi r squared. So pi r squared, and let's look at the n plus 1 concentric ring minus, to find a concentric ring, you have to subtract. In other words, you have to take the radius out to here and find that area. Then you're going to find the radius out to there, find that area, and then we're going to subtract them. So this will get me the area.
I did. I'm doing this on here.
Which is one of the zones.
So you see how much like this dude's going so fucking in long and in depth, and like you see like there's like we can this shows that this can be proven by like. I mean, because this is the shit this is like the shit at university. Like this is blah 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 blah. This is like the most in-depth thing they give us to understand this, and so just skipping so much shite, you know, not very intuitive.
The formula here, this would be, if I square this thing, put the pi in front, and I have n plus 1, this is m plus 1 lambda L, and then this other one has the pi, just square this thing, get the same thing here. That's under that radical sign. And notice that the m parts are going to cancel, and you're going to get here pi times lambda L. But now lambda L, when m is equal to 1, you get lambda L. That's like the first case. So in other words, this is the first case. So this is like the first zone. But this is a very, very interesting effect. It's showing that all the concentric rings are constant, like it's the same area. Same.
Because however, like he says that, but like, because like it's not, our assumptions are incorrect in this regard. They are all not the same area.
It's showing that all the
So it's a very weird proof to do.
Same area.
It's like useful
Same
for
area.
calculations, but it's just
It's
straight
R1
incorrect.
effect. Isn't that wild? So that's a very, very nice effect. Now, if you look at, say, this formula here, you could solve for m, and that will tell you here, if you take this radius, general radius square, and divide by lambda L, this will tell you what zone you have.
No one's tuned in at all.
And that's
How sad.
sometimes referred to as the Fresnel number. You basically take an R squared, some like general R squared of your choice,
Fresnel
and
number.
just divide by lambda L, just see what you get. All right, and that is the Fresnel number. Let's write that down. Fresnel number.
Well, I'm
And
fucking
just like plugging
vibrating.
some
I
numbers
have
and
way
check
too
it
much
out.
caffeine.
Suppose you had capital R is 1 centimeter, just to plug in some numbers, and say the Z prime and Z in the laboratory, oh, let's say they're 10 centimeters, 10 centimeters, the Z prime's over here, 10 centimeters to the left, Z's on the other side, 10 centimeters on the other side, it's close range, say, there. And then say that the lambda is, let's just pick somewhere in the middle of the spectrum, 500 nanometers. Then the first thing to do is find that L. But remember, that L is given by product over sum. So if we use this formula, L, the product of the Z's over the sum, since they're both 10, you have 10 times 10 over 10 plus 10, which is 100 over 20, which is 5. So this L is 5 centimeters. We said the R was 1 centimeter, so that means for the Fresnel number, you would have for the 1 centimeter 10 to the minus 2, and that has to be squared. And then you would divide by the 500 times 10 to the minus 9th times here 5 times 10 to the minus 2, because the 5 centimeters is going to go there. The wavelength is going here at your nanometers, 10 to the minus 9th. And the 1 centimeter is up from the top. So this is going to be equal to, up top, 10 to the minus 4. And then you're going to have 5 times 500 is 2,500. And you're going to have 10
Let's see if I'm right. 4 times
to
10 to the
minus
3 I
11.
got.
So we'll make this,
No, I'm retarded.
this is 10 to the minus 4. We'll make this down here 25. So it's 10 to the minus 9. Put the two zeros go in there, knocks minus 11 down to minus 9. And that's going to be equal to 1 over 25. Now you subtract the exponents here, you're going to have 10 to the 5th. So you have a minus 4.
Oh my
minus
god, I'm actually onto
5,
it.
so it's
4 times 10
minus
to the 3.
4. And that's going to be equal to 100,000 over 25. If you just look at this part,
Oh my
25
god.
is 104 times.
Oh, 4 times
So
10 to the...
that'll be
Holy shit, I'm on the
4,000.
ball here. Let's fucking
Wow,
go.
that's a big number, huh? See, those wavelengths are small, so you take a centimeter or something, wavelengths are small, you can get a lot of Fresnel zones in there. What is the radius for the central? Using the formula, m is 1, so you're going to have the square root of lambda times L. Alright, that's what you're going to have for that. So if you do that, we're going to have here, this is the square root of 500 times 10 to the minus 9. And the L was 5 centimeters, so that's 5 times 10 to the minus 2. So that's going to be the square root of your 2,500 times 10 to the minus 11, which is the square root of 250 times 10 to the minus 10. By taking one of those zeros, multiplying in, you get that minus 11 10 to the minus 10. And here, this is very, very close. If you're doing two significant figures, this will work. 256 is going to work. And then when you take the square root of that 10 to the minus 10, you get 10 to the minus 5th, like 5.
I don't do like these like maths dudes that like no calculations.
16.
Yes, lad.
I did that. So
1.6 times 10 to the negative 4.
16 times 10 to the minus 5. That's like saying 0.16
Kill yourself.
times 10 to the minus 3. So that is 0.16 millimeters.
Yes.
Interesting. Larger than we might have originally thought. Almost 0.2 millimeters. So let's go back to that Fresnel number again. That Fresnel number is r squared over lambda times L. If we look at a diffraction gradient, modern diffraction gradient now can have 100 lines easily per millimeter. So if that's the case, then your distance here is going to be approximately, this is 1 line per micrometer, because if you take the 1 millimeter and divide by 1,000 and slit, and each one number, for this Fresnel number here for the we're doing talking very much less than 1. That the Fresnel number is very much less than 1 when we're talking like the fraction gradient, which we did for Fraunhofer. We were doing Fraunhofer analysis. We were analyzing the diffraction gradient. So if we just plug in some numbers from like our diffraction gradient problem, you're seeing the Fresnel number is a lot less than 1. And that's consistent here by saying that the r squared over the L is a lot less than that wavelength. And that's similar to what we saw earlier. Since this r squared over L, the r squared over L, remember, is related to your delta. It's the r squared over L. So that's saying that the optical path difference, see, a lot less than lambda for diffraction gradients, Fraunhofer around. That just confirms what we already know. U4.
Here we go.
The unobstructed wave. So here, if you look at those Fresnel zones, you're going to have, like the first one, say E1, and then the next one's going to have a minus sign. So we're going back to here, that at this point P...
Actually, I might have really done this before. Let me see if I can skip most of this. If he gets to this, basically it's like half of E1, yeah. Let's see if I... Oh, what the... Oh, we're getting to the fucking circle! Oh, we're getting to the circle, yeah, okay, watch this.
C3 over 2, and then group this one, E3 over 2.
Because like one thing I disliked, so what about this one is that I disliked was it's a change the amplitude of the waves change in accordance to obliquity factor, which is 1 plus cos theta, and in the range from 0 to 180 degrees, 1 plus cos theta goes like this. So at the first part, its gradient is decreasing. It goes like this, and the gradient decreases to a point, the inflection point, then it starts increasing again. And like, if the gradient is decreasing, then it assumes that because it just makes sense. If the gradient is if the second derivative is negative, then E1 the if you think like very more thin, or like loads of small, you know, points. This point here, if you imagine it, yeah. If you have the what it's saying is like this point, and this point. What's saying is that like these two added together one plus 3, or I say amplitude 1, amplitude 3 is greater than the amplitude of 2 amplitude 2s, because like as the rate of change is decreasing, this dip is smaller than this dip, because the rate of difference is getting smaller as you go along. Is alright. Am I correct on that? Oh shit, I don't think nah, I don't think I am actually. What was this? If they say it was all greater than 0. Must all be positive. Yeah, which implies that this plus this is greater. But that doesn't make sense. Yeah. Why is that true? That's positive, yeah, it's positive. No, wait. Yeah. So I just did my calculator there and imagine like, I did I did pi over 4, 2 cos pi over 4 minus cos pi over 4 plus like 0.0001 minus cos pi over 4 plus 0.0001, and that gave me a positive answer, therefore implying this is greater than this, which is the exact opposite of what this says. So what's he here to say about this?
4 plus E5 over 2, like this. Still got the same thing. Got an E1 minus E2 plus E3 minus E4. But see, this is the amplitude due to that second zone, and this is like this is taking an average of the neighbors, and that's going to be close to 0. That the one here is going to be like E2 is going to be like close to the average of the two neighbor ones, so this is 0. So the effect is going to be E1 over E2. We say unobstructed because now we have no obstacle.
They just say close to 0, not positive or negative.
If we do that, we can consider this as the unobstructed wave. So for the unobstructed wave, remember the irradiance is always 1/2 times the amplitude squared, or you have to take the magnitude of the complex. number, and then square that. So this is 1 4 times 1/2. I'm just writing the one. This is going to be 1/8. That, like E2 is going to be like close to the average of the two neighboring ones, so this is 0. So the effect is going to be E1/E2. We say unobstructed because now we have no obstacle. Like we're just looking at the whole thing. All right. So if we do that, we can consider this as the unobstructed wave. So for the unobstructed wave, remember the irradiance is always 1/2 times the amplitude squared, or you have to take the magnitude.
Hmm. Yeah. Okay. Yeah. I see.
To the complex number, and then square that. So this is 1 4 times 1/2. I'm just writing the one. This is going to be 1/8. I'm going to write it like this because what this is showing you. What this is showing you is that this here would be the effect of the first zone. And what we're saying is that the irradiance here for the unobstructed wave is the same as 25% of the effect due to the first zone.
Let's look at the phasor diagram, sometimes called the vibration curve, in conjunction with the Fresnel zones. Now, the first Fresnel zone is the one that has radius R1. That's the circle here in the middle. And the top of it is where you have the lambda/2 out of phase point. And that begins the second Fresnel zone, which goes from lambda/2 to 2 lambda/2. Now, you can think of this Fresnel zone as consisting of subsections, where the key here is when you get to the edge of the zone, you're out of phase, so that's here, pointing to the left. And if you start down at the middle here, you can think of a vector down here pointing to the right. And then as you go up, 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 up to the edge, you have these little vectors that are going eventually to point west. And then the total effect of that first zone is E1 that goes up
As 20.
Let's look at the phasor diagram, sometimes called the vibration curve, in conjunction with the Fresnel zones. Now, the first Fresnel zone is the one that has radius R1. That's the circle here in the middle. And the top of it is where you have the lambda/2 out of phase point. And that begins the second Fresnel zone, which goes from lambda/2 to 2 lambda/2. Now, you can think of this Fresnel zone as consisting of subsections, where the key here is when you get to the edge of the zone, you're out of phase, so that's here, pointing to the left. And if you start down at the middle here, you can think of a vector down here pointing to the right. And then as you go up, 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 up to the edge, you have these little vectors that are going eventually to point west. And then the total effect of that first zone is E1 that goes from the bottom to the top, since you just add up all these vectors. You're starting down there, and you end up here, you have E1. Then when you go from the beginning of the second zone to the end of the second zone, you're going from pointing west to back at the end here is where it's going to be lambda. That's in phase, pointing east down here. And because the vectors are getting smaller, you're getting farther and farther away from the center, you come back here a little bit above, where you started. So then to go from the top down to there is the strength of the second zone. And notice it's basically out of phase with the first zone. And then for the third zone, you would start here, you're pointing east, and then when you get out of phase, you're going to be pointing west. So that's the end of the third zone. So the third zone goes from the bottom here up to there, and you are essentially adding all these vectors up, and you're going to wind up in the center, and this is the result of the unobstructed wave where all the zones contribute to the point P. You get the strength. Notice that this is 1/2 the strength of the first zone by itself. So that means that if you looked at the first zone by itself, if you were to block out all the zones by having an aperture, then you would have something that's twice as long and 4 times as bright when you do the square.
4 times by, yeah, because proportional to amplitude
And then
squared.
if you were to, let's say, blocking the first zone, so you don't have this, then here's your total when you had everything. If you knock out E1, you take this vector and subtract E1 from it, and you'll be pointing south the same length. So that means the total here minus this one is going to be pointing down, half the size of E1, same strength, which means that by blocking E1, you're going to have a vector that's equivalent to the length of unobstruction, which means you're back to being here the unobstructed case. So the unobstructed case is this one here. So that means you're going to see a spot. You'll see a spot behind the obstacle. However, when you move this point P, these lengths and Fresnel zones change, and then you can get a dark spot. They can alternate. But this helps to understand the phasors in terms of the Fresnel zones and how it all works together very nicely.
So the unobstructed wave, then by definition, no obstacles, is going to be 1/8 times E1, the length of E1 squared. And you can write that as a vector form, that EP as a vector is equal to the E1 over 2. You can make it as a vector. U5, the circular aperture. For the circular aperture, and we're going to stay on the axis here, because we've been analyzing things on the axis. What we're going to know that P, if that's the case, but then if your aperture were a little larger, so 2 zones come in, well, remember that next zone has that lambda over 2. Then EP will equal E1, like full blast, like all the other zones are gone. So if that's the case, wait a minute, 4 times then metal. And the Fresnel zones have like different sizes, and you can get this similar effect as you move around. It grows to have the changes now. Now we blocks out inner zones. So that this is then just minus E1. Now historically, the obstacle. Now historically, the obstacle. Now, historically, this idea of waves and interference was new. Thomas Young did an experiment in 1801, and here, this is the effect that you have white light, how the interference pattern occurs. We already analyzed this problem in detail. And we got, this formula here, and Thomas Young can be thought of as the beginning here of taking the wave idea seriously. Amazing person, a physician, a medical doctor, and a physicist. Spoke many languages, several languages, and did work on the Rosetta Stone, which had been discovered by Napoleon's army in 1799. And years later, when he became interested after he around 1814, and he virtually unlocked the key, understanding the most difficult of the languages, because this Rosetta Stone had like different languages. The hieroglyphic portion was the one that had the most serious challenge. So there's this competition set up. We have some powerful judges. We have Laplace, Bayet from Bayet and Savart fame. We have Poisson, Gay-Lussac, the chemist and physicist, and Arago. These are all French, and he's the chair of the committee. And they invited articles on light, and Fresnel submits. And Fresnel submits a paper on the stuff we're talking about here, the wave aspects of light. And Laplace, Bayet, and Poisson don't believe in waves, they believe in the particles. And Poisson doesn't like the paper. He believes the paper is wrong. So he uses the paper to show what we just did, that there's could be a spot behind the obstacle. And he says it's ridiculous. You can't have a spot behind a shadow. So he's ready to vote him down. But Arago, the chair, not so fast, actually sets up an experiment to check it out and finds the spot. And the spot is now called the Poisson spot, or the Arago spot, or the Fresnel spot. Poisson, in other words, trying to knock down the model, prove that Fresnel's equations don't make any sense, actually helped verify the model. So Poisson was not happy with that. He had to admit he was wrong because of science. Okay, and here you have it. There's the Poisson spot, a little spot, and here's more, a simulation where you have the spot in the middle. This is with 633 nanometer helium neon laser, 1 meter behind the disk, with the disk diameter of 4 millimeters, 2 millimeters, and 1 millimeter. Very nice. We see that, and if you do that, P will equal E1, like full blast, like all the other zones are gone. Remember, there's over here, and you're still going to get to the point over here and have interesting effects. So, if you were, for example, to just block zone 1, well then the point here, you would have, so when you had all the zones, you had this, E1 over 2. So you could think of the first zone being E1, and all the other zones subtracted in E1 over 2, and that's what you got. So this is zone 1, and these are all the other zones subtracted, because we know that this is what we get when we have all the zones. We already worked that out. But now if you block out E1, you get the same thing. In other words, EP is then just minus E1 over 2. You get the same thing. just has a phase change, but then when you do your square to get your radians, that minus sign is going to go away. So now this is amazing, because this is saying that you can get a bright spot right behind the obstacle. Now historically, this idea of waves and interference was new. Thomas Young did an experiment in 18.
Amazing, amazing, amazing.
We're going to make is that the R prime is the rho, and the R stays the same. So there we have it. So the approximation we're going to make is that the X and the Y that gets you to this little place here, like if you go say an X and then you go up to Y, that these dimensions, like these lengths, are small compared to these big ones, like the rho naught, R, and R naught. So if that's the case, we're going to now write down some equations. We're going to write down, for example, the rho is going to be the square root of, we're going to look at this, the triangle here. This little piece here is going to be x squared plus y squared. And then 0, y squared, 1/2 power. And since the x and y are small compared to this, we're going to be able to replace this
I think like
part here.
sleep's meant to help you recover from
1
illness.
plus,
And so I'm
1/2
just straight not going to recover from this illness for another while. I'm just delaying it.
squared over rho naught.
I do think like was it a quote from Civ 5 or Civ 6? It's like, well, it's obviously not, I mean, it's not from there, but you know, it's using there. Some famous dude is like, you know, if one does not find time for rest, one will find time for illness. I mean, there's no, it's true.
Plus y squared over 2 rho naught squared, like that. And then you can put the rho back in, and if you put the rho back in, you'll find that rho is
The sun is now
rho naught
rising.
plus you'll have here x squared over 2 rho naught plus y squared over 2 rho naught. And if we do the exact same thing with the r, to find the r on this side, you get the same equation where you replace the rho with r's. So let's look at that over here. We have the two equations. The rho is rho naught plus x squared over 2 rho naught plus y squared over 2 rho naught, and the exact same equation with the r would be an r naught plus x squared over 2 r naught plus a y squared over 2 r naught. That's for the other side, because you have, you know, here's your rho naught, here's your r naught, and then you did something like this, you know, where you had your rho up here and your r, and then this side here, if you square that, that's where you get the x squared plus y squared. Make the approximation, we're all set. Now just remember that this is where we're going. EP is E naught over rho naught R naught. I like to write the rho one first since it's on the left. And then we're integrating e to the I k rho plus R dA. So this is all of our equations, like we're all set here. And this is a Fresnel approximation to do this. And now we want to add these together to put them up in there. All right. So you add these together, the rho plus the R, you're going to get a rho naught plus an R naught And then plus, now let's see, we're going to have the x squared plus y squared over the rho naught, x squared plus y squared naught. So we can take the x squared
This is the
plus
same
the
thing,
y
yeah, but in
squared
2D basically.
over 2. And that's going to
Yeah.
be 1 over rho naught plus 1 over r naught. So since you have x squared over 2 and y squared over 2, and you have a 1 over r naught, that's this one. X squared over 2 plus y squared over 2, and that's over the rho naught. So like that's it. And then if we want to add these together the usual way, like this, we would get rho naught plus r naught, the sum over the product. Okay, so now all this stuff has to be put up in there. So there's a lot to write out here. EP is going to be equal to E naught, rho naught, R naught, integration over the area, E to the I, K. Now we're going to put all this stuff has to go in here. So let's just do it like that, for now. And we can see that this part's constant. So I can pull that out. And if I pull that out, in other words, I can pull out IK, the rho naught and the R naught part. Because see, this is going to be, there's an exponential here, an exponential here, there's an IK, an IK, and so this is going to be there, and all that's going to be up in there. So I can pull that out, absorb that into the constant, and don't worry about that constant. We're going to absorb stuff into constants a lot, and then we'll normalize things and show you what that constant means at the end. So here we would have then E to the IK. We would have this second part. So that would be x squared plus y squared over 2. And then here, rho naught plus r naught over rho naught times r naught. There. That looks a little bit more manageable by absorbing constants into constant. So now here, what we're going to do is write out specifically the integrations over here. This little dA is your dx dy. That's that cute little patch. The cute little patch up in here is a little dx, that's the x direction, and a little dy. So that means we're going to go from some x1 to some x2, and from some y1 to some y2, e to the ik. And here, I'm just going to write down everything again. Here, rho naught plus r naught over rho naught r naught, and dx dy. Okay, now here, what we're going to do is the convention, and this is a beautiful convention as you'll see this unfold, is that the x squared term here, take the x squared over 2 and say multiply here by k, like this, and then take the r naught and rho naught. We take this, we're basically pulling out the x squared part here. So this is going to multiply the I. See, this is suggesting to define another variable to clean things up. Remember, your k is 2 pi over lambda. It's our definition of k. You have x squared here over 2. And then you have this factor here. I'm going to rearrange things slightly. this is the convention that has been chosen, and you'll see it's a beautiful convention as we proceed. We're going to leave the pi over 2 and put the 2, we're going to put the 2 in with these constants. So that 2 goes here, pi is there, lambda, we need to get lambda somewhere, so let's put lambda there, and then that 2 is here, the other 2 is down there, and then you got all this stuff there, so everything looks good. So it's suggesting that we define a new variable so that this is all u squared. All right, don't worry about the pi and the 2. You'll see how that comes out nicely later. This is convention, so could have been done differently historically, but this is the definition of this u variable. And the v would go with the y squared. The y squared one would be similar to get the v squared. Now, when you do this, you're basically saying that when that happens, this exponential is going to look real cute. It'll be I pi
Real
over
cute.
2, and you'll have u squared plus v squared. Because there's the pi over 2, and there's the u squared, and the I is still hanging around.
Mm.
And that's going to factor real nice into these 2 dimensions like this. Now, when you look at the dx, dy, you got to replace that with a du, dv, okay, du, dv. But here, if you were to look at the definition of x, the x definition, or the u definition rather, the u definition is when you take the square root, you have x, and then you have all this stuff.
I got constants in there, so it was just chilling.
Square root sign. And then you'll have the v1 with the similar, actually the same, square root thing in there. Okay, the point is that when you replace the dx, dy, you're going to have a du, dv over a bunch of constant stuff. So when we do that, we're going to absorb all those constants in a cavalier fashion with the other constant. So we'll have constant c. Just throw all that constant stuff in, and then you'll go from u1 to u2, e to the I pi u squared over 2. And we'll go ahead and separate these, the du. Then we'll have a v2. And we'll go ahead and separate these, the du. Then we'll have a v integration, v1 to v2. E I pi v squared over 2 dv. Now that looks really nice. And this is the beautiful equation. You know, if you want to put a prime there, say, all right, technically that constant.
Yes, I really wanted that prime to be there.
Constant. So now, this is the setup, and this brings us to the Fresnel integrals. So V3, the Fresnel integrals. These integrals, even though they look simple, they cannot be done in a simple way. So if you look at one of these, e to the I pi u squared over 2, that integral can be written using the Euler relation as 2 integrals. Cosine pi u squared over 2 and then there's going to be here an I times the sine of pi u squared over 2, using Euler, du. So this naturally appears like in two places, the same kind of a formulation of stuff. So the cosine integral, when you integrate this one, the cosine, and this will be it. I'm going to write this down as integrating from 0 to u as sort of a standard formula. And then we'll have the S to represent the sines. Like the big C stands for cosine, and this is like the sine one. Integrate from u 0 to u, some like generic integration. Sine pi u squared over 2 du. Now you might say I shouldn't do this, that I should put like a prime here since I'm integrating, and like, what are you doing? Like, you're integrating over the same thing, using the same thing twice. But you know, physicists like to do this. Look at this work formula. Work is force times distance, all right, dx. But force is mass times acceleration. But acceleration is dv dt dx. Now if I let these be finite deltas, I can then start shifting deltas around and then put them back at the end. Mathematicians don't like you to move these around unless they're finite deltas, like delta v. But to be a little cavalier, and I'll have the delta x, delta t, and the dv like this. But if you do it with deltas, you can do it and then put back differentials. So this is equal to mv dv, and then often what physicists will do is they'll integrate from 0 to v and have the same v there, and this gets you then v squared over 2, and you get the famous derivation of the kinetic energy formula for the work energy theorem. So don't worry about using the same variable. I mean, if you want, you could put a prime there and a prime there, but then it's going to mess up my square with the prime. So this is fine. This is done a lot in physics. So no big deal. So what do these integrals look like? Well, here you have a plot of the integrals, the cosine one and the sine one. So these are integrals, and you're integrating from 0 to u is what you're doing. These are the results. Isn't that cool? Very nice stuff. Now we'd like to try to understand this a little bit, what's going on. So let's look at one of these integrals. The cosine of pi u squared over 2 du from 0 to u. Suppose that the u is small. So if the u is very small, then the cosine of a small value, a radian value, is going to be like 1. So that means this thing is like integrating, for the small case, from 0 to u. You're integrating 1 du. Well, that's going to be u from 0 to u, and the answer is going to be u. That's it. But see, that means that this big C of u, the cosine integration, is approximately u. Straight line. Hey, look, straight line. In fact, if you look at this, this is 1, up here is 1, and this is straight line. This is like the function here is this cu function is equal to u. It's like saying y is equal to x. It's like a straight line. You go from 0 to 0 to 1 to 1. Isn't that cool? And look, that's pretty far out there. That thing worked out pretty good, man. Look at that. So that helps us understand things a little bit better. And then if we were to look at, say, the SU one for small u. This is the sine case, where you have the sine of pi u squared over 2. And this would be, approximately the sine of a small angle theta is like theta. So that means this would integrate out. You would have the integral from 0 to u. You would have then, you just put this is like theta. Just put the theta down again, like this. And we can do that integral easily. That's going to be a cube. So that's going to be pi over 2 u cubed over 3. And when you evaluate from 0 to u, it's just going to be that. Like, we're done. We're finished. That's it. So since pi is close to 3, this is like saying u cubed over 2. Now, u should be small, but I'm going to be bold, and I want to pick u to be 1. If u is 1, then s of 1 should be 0.5. Now, I really shouldn't be working for this, but look, if I go here where I pick u to be 1, all right, then you find that here, this is u down in here, so there is u as 1. And if I come up here, look at that. That's the red one. It's almost 0.5. Like whoa. So this is u cubed. This is the cubic function. See, this is u cubed. So, isn't that wild? And it's almost reaching the 0.5 at 1. So, like, we understand, see, these graphs, these Fresnel integrals quite well by studying in detail the small u realm. So note that our results here, if we look at this one here, wish we're going to plot this in a second somewhere else, that if you look at what happens when you put in 0, like you don't integrate at all, then the integrals come out to be 0. Like you didn't integrate at all. In other words, you went from 0 to 0. And so they're both down here. That makes sense. And then let's go ahead and put in our result where we had 1. When we had 1, our result was that we would get, we would get 1, but at this point, let's put in what the value for 1 really is. It's really close to 0.8. So, because this is pushing it too far. So this is basically a 0.8. And then this, we'll leave this as 0.5 because that's pretty close to 0.5. So there we go. So we have two summaries here of our work. Because now the fun begins continues with the Cornu spiral, also called the Euler spiral, where you plot. Now what you do is you plot the CU, and that's an integral already done. Let's go ahead and remind ourselves that that's an integral. That's the cosine of pi u squared over 2 du. And the sine integral, these are the capital letters that represent the integrals. So 0 to u of the sine. Now we're doing pure math now, in a sense, because we're going to need these in the Fresnel diffraction equation. That these show up, so we want to just we're taking a pause here to study the math, because can't do the integrals. So here, if we're going to plot, we're to do a plot in the complex plane, because remember that the integral that we're interested in is going to be the cosine 1 plus I times the sine 1 when you do the Fresnel stuff, when you do the physics. And now we're going to look at the result. This is what you get. When you plot, it would be the cosine 1 plus I times the sine 1 when you do the Fresnel stuff, when you do the physics. And now we're going to look at the result. this is what you get when you plot the cosine integral along the real axis and the sine integral along the imaginary axis. Now this is an amazing thing I'm going to show you, that if you were to like do an arc length, here, where the arc length, like a ds squared in calculus is a dx squared plus a dy squared. Here you have a dc squared plus a ds squared, because that's what you're plotting, c and s, and there's the c and there's the s. But a dc, that's undoing that integral. That's going to be cosine pi u squared over 2 du. And the ds, we're just going backwards. If you integrate this thing, you get then the c, and then you get the integral. But we're taking a differential. This is sine, let me go ahead and do that, pi u squared over 2 du. But now, check this out. If you square these things and add them up, because that's what these things are here. This is the ds, the height. This is the dc, because this is like your x coordinate. This is your y coordinate. But if you square them and add them up, what's cosine squared plus sine squared? There's 1. So in other words, the dc squared plus the ds squared is going to be 1 times the du squared. That means this u parameter is being realized as the arc length. That is wild. That is amazing. In other words, the arc length of the graph is du. So the u variable can be represented here. See, there's 0, there's a u getting bigger, u going negative. I would like to make now 8 observations on the Cornu spiral. And I have these in the notes here for you, all written out. The first one is to check if our result from before, if we put in 0, don't integrate at all. So the u variable can be represented here. See, there's 0, there's a u getting bigger, u going negative. I would like to make now 8 observations on the Cornu spiral. And I have these in the notes here for you, all written out. The first one is to check if our result from before, if we put in 0, don't integrate at all, that you're supposed to get 0, 0, like you didn't integrate at all. Well, yeah, there it is. Like, that's the point there. So if c is 0 and s is 0, like, that's the point. It's right there. Now, what about our other case? We said that at a c of 1 and s is 1, so this is a second observation here, was roughly a 0.8 and a 0.5. So let's look for that point. We want the c to be a 0.8, so you come over there's the c, and you again go up, and there's the 0.5. See, it's like it's up here, and look, the u is 1. And this is observation 3. If you take this thing and wrap it down like this thing would probably come out to about there, And guess what's out there? 0.8, 1.0. So isn't that amazing? Look at that. You just take that thing and unwind it. So this is a measure of the U. Observation 4. We found that for small u,
Uh, I'm going to I'm gonna go get a shower now.